Welcome to science class. Today we will begin learning about meteorology, which is the study of the composition, structure, and dynamic activity of the atmosphere. The atmosphere is by far the smallest portion of our planet, but it is the portion of Earth that changes more rapidly than any other. And while it is a small portion, it is by no means insignificant. If Earth had no atmosphere, it would have no oceans and no life. If the atmosphere was not dynamic, there would be no weather cycles, and therefore it's likely that complex life would not have evolved, or it would never have evolved to the extent that it has. There are only 400 molecules of carbon dioxide for every million atmospheric molecules, which is tiny, but if that number was half, then Earth would be much colder, and most of the land north of 45 degrees would be covered in ice and snow permanently. If that number was twice as large, then it's likely that after thousands of years, there would be almost no ice whatsoever on the planet. What we find is that in the atmosphere, small changes make a big difference. Let's get started. In this first meteorology video, we are going to take a look at the composition and structure of the atmosphere. Earth's atmosphere has undergone radical changes. The earliest atmosphere on Earth, some 4 billion years ago, would have been composed of the same kinds of materials we find in volcanic eruptions: hydrogen sulfide, methane, and carbon dioxide. No pure oxygen would have been found. Only life is capable of generating pure oxygen in large quantities. The first oxygen that would have been produced would have been absorbed at first by iron in the oceans, and then by the oceans themselves. Scientists think it wasn't until 2.5 billion years ago that oxygen began to accumulate in the atmosphere. The majority of those molecules in the early atmosphere gradually became absorbed by living things, the oceans, and sediments. At times, Earth's atmosphere has contained nearly twice as much oxygen as it does today, and well over 12 times as much carbon dioxide as it does today. It depends on a huge number of geological, biological, and astronomical factors. Today, about 99.95% of the volume of Earth's atmosphere is just 3 gases: nitrogen, oxygen, and argon. Most of the atmosphere is nitrogen, but the source for that nitrogen is a mystery. We really don't know what the source is or was. You might think that trees are responsible for all of that oxygen in the air. Fact is, if all trees on Earth disappeared, the amount of oxygen in the atmosphere would barely change at all. Photosynthesis is the process that makes oxygen, yes, but trees have mitochondria, and they use virtually all of the oxygen they produce to metabolize the carbohydrates they make during photosynthesis. Now, to be clear, it would be very bad if all trees disappeared, but not because we would no longer have oxygen to breathe. In reality, microscopic life in the oceans produces the majority of all atmospheric oxygen. They create much more than they use. The gases that make up the remaining 0.05% of the atmosphere are by no means insignificant. We call these variable gases because their concentration varies. Like I said, small changes make a big difference. The levels of methane, water vapor, and carbon dioxide have a direct effect on the amount of heating trapped in Earth's atmosphere. But there's also dust particles, material ejected from large eruptions, ozone, and man-made chemicals, which otherwise normally wouldn't exist at all. Dust particles are essential for cloud formation. Droplets of water require solid particles to cling to. While these dust particles are microscopic, compared to water droplets in the sky, they are huge. Water collects around these condensation nuclei, as they are called, and that begins the snowballing effect, we could call it, that forms droplets of precipitation. Ozone filters a large amount of the UV radiation that would otherwise be catastrophic for life on Earth, since it causes harmful mutations. The variable gases that humans are responsible for are complicated. Some of them are directly created by us, and could never exist in the atmosphere if it weren't for us, such as chlorofluorocarbons, or CFCs. CFCs are a pollutant, and pollutants are any material that directly and negatively impacts the usefulness of a resource. CFCs, it turns out, destroy ozone, so they have been phased out. While CFCs are not directly harmful to humans, they are indirectly harmful to humans in a big way. Secondary pollutants are those which form as a result of chemical reactions in the atmosphere. For example, humans release sulfur dioxide gas, which reacts with oxygen in the atmosphere to form sulfur trioxide, which reacts with water to form sulfuric acid. We do not directly create the sulfuric acid, but we are responsible for its creation. The energy from sunlight in the atmosphere can also trigger our emissions to chemically react and form new harmful substances in the atmosphere as well. While carbon dioxide and methane are not pollutants, they are still classified as potentially harmful emissions because they lead to global warming, which does have negative impacts on human beings. So that pretty well covers the composition of the atmosphere. Now let's talk about the structure of the atmosphere. The atmosphere is made of gases, which makes its structure highly unique. The atmosphere technically extends over 10,000 kilometers into space, but the molecules are so thin at that point that we can essentially pretend it's not a real part of the atmosphere. We will only focus on the first 100 kilometers of the atmosphere. Because the atmosphere is made of light gases, and because of Earth's gravity, 90% of the atmosphere's mass is found in just the first 22 kilometers. This is the altitude at which basically all relevant atmospheric processes, such as weather, occur. Half of all molecules in the atmosphere are concentrated in just the first 5 kilometers, and above 100 kilometers, only 0.00003% of the atmosphere in terms of mass still remains. From bottom to top, the layers of the atmosphere are the troposphere, stratosphere, mesosphere, and thermosphere. Above the thermosphere is the exosphere, which extends all the way out to 10,000 kilometers, but like how Pluto isn't really a planet, I'm going to say the exosphere isn't really part of the atmosphere. It's a well-known fact that as you go higher in altitude, it gets colder, but that pattern does not continue forever. At an altitude of about 12 kilometers above sea level, you hit what's called the Tropopause, where the temperature does not increase or decrease for about another 10 kilometers. This boundary, where temperatures do not change, marks the end of the troposphere and the beginning of the stratosphere. At an altitude of about 22 kilometers above sea level, the temperatures begin to rise again. Close to 50 kilometers above the surface, where the atmospheric pressure is almost undetectable, the temperature is above freezing. The reason for this is because ozone is concentrated in the stratosphere, and ozone absorbs UV radiation, so it has its own kind of greenhouse effect. 90% of all ozone molecules are concentrated in the stratosphere. Then at about 50 kilometers above sea level, there's another temperature pause, the stratopause, which marks the beginning of the mesosphere, and temperatures then begin to plummet. Once again, at this altitude, the air is so thin that air pressure is almost undetectable. However, meteors do interact with the atmosphere here. Most meteors burn up in the mesosphere. Imagine swimming through water. It's not very difficult, even though the water offers a lot of resistance. But now imagine being dragged at 100 miles per hour through the water. The resistance of those water molecules would be extraordinary. Meteors that strike Earth's atmosphere are going at speeds that range from 11 kilometers per second to 72 kilometers per second. That's fast enough to circle the globe in 9.5 minutes. At those insane speeds, even the incredibly thin atmosphere in the mesosphere provides a huge amount of resistance. The burning up of the meteors is actually caused by the meteor compressing the air molecules in front of it and superheating the air molecules. When you compress a gas, it heats up. The final temperature pause, the mesopause, occurs at about 80 kilometers above sea level, and this is where the thermosphere begins. The temperatures in the thermosphere rise to well above the temperatures on the surface of Earth. We say that Earth is in a Goldilocks zone, not too hot, not too cold. But that's not true. If it weren't for Earth's atmosphere, temperatures would be so much different than they are. Take the moon. It's the same distance from the sun as Earth is. What are the temperatures like on the moon? On the sunlit surface of the moon, it gets to 120 degrees Celsius, while on the dark side of the moon, the temperatures drop to negative 130 degrees Celsius. Because the moon has no atmosphere, it both does not shield itself from the full force of solar rays and does not retain any heat it absorbs through a greenhouse effect. so it has extremes on both ends. Speaking of that, temperature is what we will discuss in the next video as we learn how the atmosphere is heated. Thanks for watching.